Hello students, this is Professor Anindo Dash. Welcome to the lecture on the real gas series, and we have already studied a bit of the concept of real gases and will continue with our next part. Okay, so in the previous lecture we were talking about the Amagat's plot. In Amagat's experimental plot, we will plot Z along y-axis, the compressibility factor Z, it's plotted along y-axis, and pressure P is plotted along x-axis. There are two types of Amagat's plot. Type 1 comprises the plot of a particular gas at different temperature. That's what we have already done. We have plotted it, we have made our observations, we have noted all our observations, and we have already explained those observations in context to the Van der Waals equation of state. Now we will move on to type 2 plot, where we will be plotting Z with respect to P, but for different gases at a particular temperature. So we will affix a particular temperature, T is constant, and we will be plotting different gases. We will be plotting different gases. Nitrogen, hydrogen, oxygen, methane, carbon dioxide, etc. Okay. So from this particular plot, can we compare the TB values of these gases? We know that TB is the characteristic property of a particular gas. Boil temperature TB, it is the characteristic property of a particular gas. So TB of carbon dioxide will be different from TB of methane. That will be different from TB of oxygen. Again, that will be different from TB of hydrogen, and so on. So, from this plot, is it possible to compare the TB values? The answer is yes. At first, let us ponder on this particular plot. And we see nitrogen, it's showing a special type of behavior. You see? See, this is the plot exhibited by nitrogen. So you can see in the low pressure region, in this low pressure region, what is happening? Nitrogen is not showing any deviation. So this temperature must be equal to the boil temperature of nitrogen. This temperature which we have affixed over here must be the boil temperature of nitrogen, because at this particular temperature, you see, the nitrogen gas is showing no deviation in the low pressure region, but in the higher pressure region it is showing OPD. So this must be the boil temperature of nitrogen. So this is reference. Now there are two rules to ascertain the other TB values. You see, rule 1, exhibition of UPD shows greater TB. Exhibition of UPD shows greater TB values. So the gases which will exhibit UPD will show greater TB values. Now which gases are exhibiting UPD? This one, and this one. Carbon dioxide, methane, and oxygen. So TB of carbon dioxide, TB of methane, and TB of oxygen should be greater. Now, can we compare the TB values of these three gases? We know the TB values of these three gases must be greater than the TB value of nitrogen from the first part of rule 1. Now, let us look into the second part of rule 1. Greater UPD has greater TB. So, the one with highest UPD will have highest TB. So, carbon dioxide is showing highest UPD. So the TB value of carbon dioxide should be highest. Then methane. And then oxygen. So if you remember rule number 1, then rule number 2 is quite evident. The one showing OPT will have lower TB, so TB of hydrogen is lowest over here. Done. So I've understood this one. Now students, we need to exemplify a very special case over here. That is the case of hydrogen and helium. Actually, for hydrogen and helium, due to very low size, the value of A is 0, is tending to 0. The characteristic van der Waals constant A is tending to 0. So if the characteristic van der Waals constant is tending to 0, then this part is missing. So the equation simply turns out to be P whole multiplied by V bar minus B is equal to RT. So this becomes the equation of state for hydrogen and helium. Again, if A is equal to 0, then what is the value of TB? TB is A by RB. Already I have deduced in the previous lecture. So that is also equal to 0. So the boil temperature of hydrogen is 0. It's very low. We have also found it in the previous example. I have seen that the boil temperature of hydrogen is extremely low. It's almost tending to 0. You can say it's lowest because Kelvin temperature cannot be lower than 0. So it's lowest. So you can see the equation turns out to be P whole multiplied by V bar minus B is equal to RT. So from here you can see, if you multiply this, PV bar minus PB equal to RT. Now you want to calculate Z. So you divide all the terms by RT and you bring this term to the right hand side. So it becomes PV bar by RT equal to RT by RT is 1. This minus becomes plus in the right hand side. So it becomes PB by RT. So the expression of Z is, see, 1 plus B by RT multiplied by P. 1 plus PB by RT can be written like this. 1 plus B by RT multiplied by P. Now you can say, if you are plotting Z along y-axis and P along x-axis, then 1 is the intercept and this is the slope, y equal to mx plus c. And the value of m is b by rt. So you have a linear rise of z with respect to p. So this is the special case where you will see that z, where you will see that hydrogen will show a linear rise. See, hydrogen is showing a linear rise. And you can explain that. And the slope is b by rt. Understood? Now students, we'll do a conceptual question over here. At what temperature does the slope of z versus p at p tending to 0, p equal to 0 means p tending to 0, have maximum value for a van der Waals gas, and what is the maximum value of the slope? At what temperature will the slope of z versus p have a maximum value? Students, we have already we have already expressed z in the power series of p. See, z equal to p to the power 0, the first term was 1, plus something multiplied by p to the power 1, plus something multiplied by p to the power 2. Now at very low pressure, we always neglect the third term, which contains p square. So z becomes 1 plus something multiplied by p. And what is this something? We have already reduced. It's 1 by RT whole multiplied by b minus a by RT. So at low pressure, we know that z is equal to 1 plus 1 by RT whole multiplied by b minus a by RT multiplied by p. We did this. Now they are asking at what temperature the slope of z versus p will be of maximum value, and then you need to calculate the maximum value. So at first you need to calculate a slope. So it's basically a straight line. So this is the slope. This is y, this is c, this is m, this is x. So if you do del z del p at constant, you will get the same thing. This is coming as the slope. 1 by RT whole multiplied by b minus a by RT. So it becomes b by RT minus a by r square t square. Now at t equal to Tm, let us consider this temperature to be Tm. At Tm, the slope is maximum. So at t equal to Tm, the slope m is m max. And we know that the condition of maxima is if the first order derivative is 0. So the slope is maximized with respect to temperature. So you need to differentiate this slope with respect to temperature, and then you must equate it to 0. So this satisfies the condition of the maxima. So dm dt is equal to 0. This is the condition of the maximization of the slope with respect to temperature. And you have already got the expression of m. So you differentiate m with respect to temperature. So the first term becomes b by r is a constant. You are differentiating 1 by t, it becomes minus 1 by t square. So it becomes minus b by RT square. The first term is this. And in the second term, you have got 1 by t square. So it becomes 2 minus 2 by t cube. And you have already got a negative sign, so it becomes plus. And a by r square is a constant, so a by r square remains as it is. And it becomes plus 2 by t cube. So it becomes plus 2a by r square t cube. Simple differentiation. Now you are taking 1 by RT square common. So you are getting 2a by RT minus p. Now at t equal to Tm, this term should be equal to 0. At t equal to Tm, this term should be equal to 0. So you have got 1 by Rtm square whole multiplied by 2a by Rtm minus b to be equal to 0. But 1 by Rtm square is non-zero. Since Tm is not infinity, 1 by Rtm square is non-zero. So Tm is not equal to infinity. So this term is non-zero. If this term is non-zero, then this term must be equal to 0. So 2a by Rtm is equal to b. That makes Tm to be equal to 2a by Rb. So you have got the value of the temperature. The first part is explained. Now you need to calculate the value of m max. It's very simple. We'll do it in the next part. See. M max is nothing but the value of m at t equal to Tm. So you need to replace this t and this t by Tm. I have done it. b by Rtm minus a by r square Tm square. So b by r whole multiplied by 1 by Tm. The value of Tm is 2a by Rb. So 1 by Tm becomes Rb by 2a. Done. Here minus a by r square multiplied by 1 by Tm square. So it becomes Rb by 2a whole square. Now if you simplify, you will get the value to be equal to b square by 4a. So this becomes the value of the M max. Okay. Now we'll do a few interactive problems over here. The first problem, you see, the compressibility factor of 1 mole of a Van der Waals gas of negligible A value is, what should be the compressibility factor for negligible value of A? We have already done this. Let us check the special case. In the special case, we saw that negligible value of A, that means if A is tending to 0, then the slope is B by RT. Z becomes 1 plus B by RT multiplied by P. The slope becomes B by RT. So the answer must be B by RT. Answer must be B by RT. Slope must be B by RT. The intercept is 1. So it becomes 1 plus BP by RT. The value of Z becomes 1 plus BP by RT. This is nothing but the special case. The value of the compressibility factor is 1 plus BP by RT. If they ask the value of Z is 1 plus BP by RT. If they ask the value of the slope, then it's B by RT. If they ask the value of the intercept, then it's 1. So you know the answer. This is nothing but the special case. That's what we have already done. Next problem. Maximum deviation from ideal gas is expected from which one? We have maximum deviation from ideal gas where there is maximum interaction. Greater is the interaction, greater will be the deviation. So with increase in interaction, deviation increases. Now which one of these 4 will show highest interaction? The answer is ammonia. Why? Because ammonia is the only polar molecule over here. Rest all are non-polar. Non-polar. For all this, the dipole moment is 0. But for ammonia, the dipole moment is positive. So if it has a positive dipole moment, if it is polar, then there will be greater Coulombic interaction. And if there is greater Coulombic interaction, then obviously there will be greater deviation. So the answer is ammonia. Do you understand? So in this question, they have given the expression. They have given the expression of the real gas, Van der Waals gas. And A and B are Van der Waals constants, which we know. You have 2 sets of gases: oxygen, carbon dioxide, hydrogen, helium, methane, oxygen, and hydrogen. In gases given in set 1 in increasing order of B and gases given in set 2 in decreasing order of B are arranged below. Select the correct of the following. From set 1, you have to arrange the B value. You have to arrange the B value in increasing order. And from set 2, you have to arrange the A value. You have to arrange the A value in decreasing order. This is in increasing order, this is in decreasing order. So which one will have highest value of B? We already know that B is equal to 16 by 3 pi r cube multiplied by Avogadro number. So B is directly proportional to r cube. So greater is the molecular radius, greater will be the value of B. greater is the molecular radius, greater will be the value of B. So obviously, carbon dioxide will have the highest value of B. So you can cancel out option A, because in option A you have oxygen to be the highest value. So any of these three options are correct. And which will have the lowest value of B? Hydrogen, because hydrogen is the smallest molecule. So carbon dioxide is highest, hydrogen is lowest. So this is the correct option. You don't have to look into the set 2 at all, because set 1 is giving you the correct option. So you can solve problems only by elimination method, and you can save your time. Okay. So this is how we'll solve the problems. So, dear students, thank you all for this lecture, and stay tuned for the next lecture on real gas. So bye bye for now.